So I'm going to talk about PCA double descent and some connections with Gaussian processes. The setting that I'm going to adopt in this talk is in supervised learning setting. So basically like a classical regression problem. So here we'll have some training set given by pairs X and Y. X are your data points and Y are your targets. And we're gonna have also a test set that comes from the same distribution, I guess. So our objective is to do function interpolation, meaning that we want to find the function f theta so that it predicts the values of y from x. And say we parameterize the class of functions that we are optimizing on by this parameter theta. But we don't just want to interpolate. We want to be able to generalize to our test set. We want to have something that can predict outside of the data that it has seen. So we want also to have a small generalization error. So we want that when we evaluate our learn function on this test data, we can predict the y's. And the example of the classes of functions that we are going to take into consideration include neural networks and linear regressions, and there are many other classes of functions that we can think of. This is a general setup. So this talk is inspired by this famous paper from 2019 by Belkin and collaborators that identifies this double descent phenomenon. So the idea is the following. So basically what they say is that if you have a regression problem, like the one I just introduced, and you increase the capacity of your model, then what happens is that you're going to be able to feed your training data better when you increase the number of parameters of your model. But there's going to be a point where your performance in your test set is going to start increasing. So here, for instance, you have the x-axis here is the number of parameters of your model, and you do this experiment, and you have that the training data decreases monotonically, but the test data starts decreasing and then increases again, and then at this point you have this interpolation regime where you can fit all your data perfectly, say. And then after that, if you continue increasing the number of parameters, then the test errors start decreasing again. And for some models, they did a lot of experiments with several classes of models, neural networks, linear regression, but also random forest and other class of models that people use for regression. They observed that in the overparameterized regime, meaning that when you have more parameters than data, sometimes the value of your test error is smaller than what is in the best case in the underparameterized regime. So they claim, okay, overparameterized models generalize better, which is in contrast with the classical statistical way of thinking about this problem. So in the classical literature, you typically see this curve over here. And this is also an image from this Belkin and collaborators paper, where they say, okay, if your model is not expressive enough, then you're going to be underfitting your data. And if your model is very expressive, you're going to fit your data perfectly, but then your training data is going to be fit perfectly, but you're overfitting, and your test data is not going to look good at all in your model. And I will show you some examples of that. And the classical theory tells you like, okay, there is this sweet spot where you have this bias variance trade-off, where this is the best number of parameters that you can have for a model like this. And what they claim is that if you don't stay just with this picture, go over the overparameterized regime and see what happens. So they say that if you start increasing the capacity of your model, then there's going to be some form of implicit regularization of your model that will end up giving you that the test error starts decreasing. And then at some point, you may even have that the best performance of your test error is even better in the overparameterized regime than in the classical underparameterized regime. And this is something that has been widely used to justify the use of very overparameterized models in deep learning, for instance. Okay, so in this talk, I'm going to describe some things about this double descent phenomenon, and something that I want to discuss is what does it mean to have an increasing number of features for some models, in particular in the setting of the Gaussian processes. But yeah, so this peaking phenomenon is this phenomenon where like you have like a large value of your risk on the interpolation threshold, and that's typically known as the peaking. And there has been many interesting papers after this Belkin and collaborators paper showing that actually this peak that you see in the risk occurs due to ill conditioning on the empirical covariance data, covariance matrix of the data. And typically, this is just an artifact of using certain methods that are not regularized. And if you do some regularization, then that phenomenon disappears. And the same thing happens in the more complicated settings where you cannot analyze it, but you can still maybe reproduce it, like in deep learning. Like there's some works where like you can reproduce this peaking phenomenon in deep learning, but if you add some certain forms of regularization, like early stopping and things like that, then this behavior of the peaking disappears, and you see something that is monotonically decreasing in general. So there's, in particular, there's this paper by Nakiran and collaborators in 2020, where they show that they can mitigate this double descent phenomenon using rigid regularization. So basically by just regularizing the regression. And also other forms of regularization like lasso will remove this behavior. And my paper will show, like in this low dimensional models, it's going to show that PCA dimensionality reduction, if you do some preprocessing of your data with PCA dimensionality reduction, then you can also prove that this phenomenon will disappear. So you won't have this peaking. And yeah. So let me just start with a simple example that illustrates why this phenomenon occurs. So this example is by this paper by Hasty and collaborators in 2019. Basically what they say is, okay, let's consider a simple model. I'm gonna have that my x's are a sample from a Gaussian, and my y's are going to be x times beta plus some epsilon, which is some Gaussian noise. And so basically in matrix form, I can send that y's is x times beta plus epsilon, a classical linear model. And the risk of the estimator is the out of sample prediction error is going to be the expected value for a point sample from the test set. So something that it hasn't seen, but before it hasn't been used in the training, but it satisfies that it comes from the same distribution of what does the prediction of my model says that it will be minus the true expected value under this model condition on the training data. So this is the classical computation that you probably maybe have seen in a statistics course, where you can actually add and subtract the expected value of your estimator given your data, and split your risk into terms, the bias squared and the variance squared. And for the case of these ordinary least squares, you can write it explicitly because you know what is the form of the estimator. And so, well, I'm using that the estimator for beta hat is equal to the pseudo inverse of x times y. That's what I'm using here. And this is And this is what it shows up in the computation. So then if you look at the variance, you can actually see that the variance of this estimator will not depend on the covariance of the data. It won't depend on the covariance matrix of the data. And this is a cool trick that you can do. It's like if your data is X has was some Gaussian with zero mean and variance CXX. You can write it. You can write X as some Z, which Z is just a standard Gaussian times this CXX to the 1/2. And then if you do the computation of the variance, you can see that if you do this change of variable here and you use the cyclic property of the trace, you can cancel out the covariance matrix. So basically the variance of the estimator will only depend on the empirical eigenvalues of the standard Gaussian, which is known to be satisfying the Marchenko-Pastur distribution. And so once that you know that, and you know what are these empirical eigenvalues of this, like what is the distribution of the eigenvalues of this Gaussian, you can see that actually if the number of points is equal than the number of dimensions, then with high probability, you have an eigenvalue that is very close to 0. And so when you take this inverse, you get something that blows up. And this is the reason why you have this peak in the risk. It's just because the variance blows up because you're taking the inverse of X transpose. And this matrix is very ill-conditioned, like for the Gaussian case, is very ill-conditioned regardless of the effect of the variance of X. Like, and here I have this example that I just ran in Python when I say, okay, I'm sampling from a Gaussian 75 by 75 XX transpose matrix from this Gaussian, and I look at the eigenvalues, and then the eigenvalues have this distribution where there's like some eigenvalue that is very small. And that's basically why this double descent occurs. So given that you know why it happens, then it's quite obvious that if you are going to regularize this thing where you're not going to take the inverse of XX transpose anymore, but you just say do XX transpose plus lambda times the identity, then you're not going to have this peaking behavior anymore. So that's about what is happening with the double descent. And I'm gonna switch gears a little bit, and I'm gonna explain what is the context of my project and how it connects with the double descent phenomenon. So, so this project is with my PhD student, Teresa Huang, Johns Hopkins, and a collaborator at NYU, in astrophysics, David Hogg. So David is in astrophysics, and his goal, like he came to us because he has data science problems, and one of the problems that they care about is to be able to predict the properties of some stars from their spectrum. So basically, they are given signals that look like this. They correspond to the spectrum of the star at different wavelengths, and they want to predict the mass or the temperature or the abundance of certain chemical elements in the stars. So
sorry, Soledad.
Yes.
So there was a question in the chat about the first part, so maybe I don't know if it's better to address it now.
Oh, we can address it, yeah. How does the second descent appear in the variance if the variance blows up? Well, yeah. So this is for the case n smaller than n. N is smaller than p. But when P is greater than N, then your estimator, you compute it in this form. And then when you are looking at the B hat expressed in this form, if you look at the Marchenko-Pastur distribution, this matrix doesn't have zeros in singular values. Does that make sense? Does that answer your question? Yeah. It's just because the computation is different when you do P is more than N or P greater than N. Yeah. Okay. So I was discussing about this data science problem. So basically, there's two ways of thinking about it. The machine learning way of thinking about it is, okay, you have a discriminative model. Say that you have some training data. You have this like 8,000 by 1 images, the spectrum of stars, and you know what the target values are, like maybe from like a training set, you know what the mass temperatures are for certain stars, and then you want to infer a model that will be able to predict for other stars that you haven't seen. So that would be like the machine learning way, which is a discriminative model that wants to predict the properties from the spectra. But the physical way of thinking about this problem is to do it in the opposite direction. So they want to have a physical model that is able to predict that, depending on the properties of the star, how the spectra would look like. So the model will go in the other direction. It would generate the data from the labels. And the claim of my collaborator is that actually the way to do it in the physical sciences is the generative way. You never do the discriminative way, because that's physically like the way that you use your knowledge of physics and of the world. And so his claim was that the generative models are going to be more robust to adversarial attacks, and they're going to be generally better at generalization and everything. So that's his claim, and we haven't been able to prove that claim, but I think that that's a possibility that for certain models we can actually do it. And so the simplest generative linear model that we come up with that makes sense for this specific problem is similar to a model that has been studied in the statistics literature that is called partial least squares. That basically what it does is like you consider that both your data and your labels are generated by a low rank model that is described by this latent space Z. So basically you have, maybe it's a linear model that you have a latent space Z, and then you can produce the labels and the data from this latent space. So one way of optimizing this problem is to find the best fit for the data, so that it's generated from this latent space. Subject that when you do the projection of the latent state to the label space, you can recover the label space perfectly. This is not the only way to do this, but that's just one formulation. Like, what is, if you restrict that you can recover your labels perfectly, how much can you like recover your data with this low rank model? So this model actually, if you do some simplification where you remove this constraint, basically what you are doing is like a low rank description of your data. See how well you can do this low rank description of your data, and see whether that will give you something better in terms of generalization error and this double descent. And so basically this is like the first stage of this project that we completed now, was to understand what this regression problem would look like if you do some low dimension reduction on your data. And also, I would like to comment that this approach of doing low dimension reduction of the data is used as a form of regularization in deep learning. So there's some papers that propose to do some sort of dimensionality reduction of the layers or of the data to promote some form of regularization. And in some ways, it actually provides you better estimators. And I'm gonna explain why or how. So here in this slide, I'm just describing that basically I just do PCA on the data and compute ordinary least squares on that. So this is the ordinary least squares on the PCA dimension reduction of the data. And so to make a point of how it looks like, the idea is that if we have, in this example, if we have some generative model for data where your data comes from a low rank model where like you have the empirical, the covariance matrix has a gap in the eigenvalues. So this is the eigenvalues of this covariance matrix, and there's a gap over here. Then you can show that if you do dimensionality reduction on your data, the risk never blows up, and actually is comparable with what you would obtain if you do just ridge regression. So PCA is another form of regularization that behaves in a similar way. So, and here in this plot, I'm showing the behavior of ordinary least squares, which has this double descent phenomenon, like it goes like this. Oops. This is the ordinary least squares. And then PCA and ridge regression and PCA-OLS are monotonically decreasing or almost. And the generative model has some weird behavior that we are not able to explain yet. Okay. So I want to connect this idea with many papers that are in the literature that basically are proposed as the analysis of two-layer neural networks. But it's with a trick, because the idea is the following. They consider these two-layer neural networks where the first layer, so they start with the data. Maybe I should write it here, X. X is their input. And then what they do is the first layer produces some f of X, which is the features, or yeah, this is called feature embedding. And then there is another layer that that gives you the output. So this is the Y, right? And so basically what these models, what they do is they consider this kind of like two-layer neural network, but this is trained just like using some form of regression, but this is not trained. It's a fixed model that extracts the features from the data. So for instance, there's this very nice paper by May and Montanari from 2019 that considered this feature embedding to be random features. So they extract random features, they apply a ReLU to the random features, and then they do the regression with the target data, and they analyze the risk of this estimator, and they have some closed form expression for the asymptotic value when the number of features goes to infinity. Another model that does something similar, where this layer over here is random Gaussian embedding. So this is a paper by Bag and collaborators in ICLR 2020. Also random orthogonal projections, and this paper is very nice. It's very it has all the analysis in the regularized and not regularized regimes of what happens if you do like a random orthogonal projection in this layer, and then you use that for training for the regression. There's no, as far as I know, there's no analysis for the partial least squares model. And there's also another model that is quite similar to ours, but it's a little bit different because it's an Oracle principal component analysis by Su and Xu in Europe's 2019. So what they do here, instead of doing PCA on the data, they project to the top K components of the true covariance matrix. And in that case, they show that they actually have some double descent, which is not what we observed, and that was very puzzling to us. But yeah, anyway. So basically, I just wanted to say there's many nice papers that consider this model. And in our case, what we just do is we consider the first layer is just like PCA of the data X, and then you do just linear regression in the PCA. So, and this is something that is a little bit more complicated to analyze because most of these feature embedding models are fixed, are not adaptive to the data. So if you want to be adapted to the data, it may bring some complications to analysis. So we actually don't have an asymptotic analysis, but a non-asymptotic bound on the risk. Yeah.
Soledad?
So, do you have any questions?
Yes, can you hear me?
Yes.
So, sorry, maybe I'm misunderstanding something, but my sense is that the goal at the end of the day is to understand generalization properties of these overparameterized models. Mm-hmm. And so in the specific case of regression, when the true model is low rank, we know that if we do regularization with Tikhonov regularization, we're going to get a solution that generalizes well because the linear models has been studied through other means. And so we know that the minimum normal solution generalizes well. Mm-hmm. So coincidentally, that's equivalent to actually reducing the space to PCA and then solving. Mm-hmm. And so my concern is that by letting the first layer be PCA, we are sort of helping, the whole point I think was to pretend I don't know what the effect of parameterization is and figuring out whether the learning dynamics will bias the solution to converge to the manifold that generalizes well. And so what I'm trying to understand is why would I want to analyze the PCA regime? Because that's, these simpler problems are just meant to study the more general case. And in the more general case, we're not going to know what the right embedding should be for the first layer.
Yeah, I mean, sure. That's a good point, but it is true that in most of the physical sciences, the approach is not necessarily to do some like complicated deep learning model, but just like do some sort of dimensionality reduction on the data and then do that for processing. So I mean, and we saw this in like the previous talks here. So I guess that, yes, what you're saying is that understanding this regime is not going to be helpful to understand the role of overparameterization in deep learning, and I agree with that point of view. So yeah.
So no, maybe I would say that it is providing the analysis additional is sort of already restricting the analysis to the right manifold that generalizes well. And I think that's one part of the story, but in the more general case, You want to understand also the effect of the implicit bias of the optimization algorithm together with overparameterization. And in that case, you therefore have to worry about converging to the manifold of solutions that generalize well, in addition to convergence within the manifold. And I think that the restriction to PCA is already giving half of the information to the analysis, which we know in this particular case of regression with the square laws, but we don't know in general.
I mean, I'm happy to take this conversation offline, but yeah, it's a good point. Yeah. Mm-hmm.
Great, thank you.
No, thank you. Okay, so maybe this kind of answers your question here. Like if you look at the performance of all these methods that, okay, I understand that had been proposed to be a proxy of the analysis that one would wish could do if you could analyze a multiple layer neural network, but that's much harder. So you say, okay, I'm going to do a random feature in the first one and then analyze regression with the random features like that, say for instance, or something like that. But if you look at all these regression models and you see how they perform experimentally for this specific problem, you see that all these models have like they exhibit this peak on the, like because they are not regularized, and also they all converge to the same thing, even with PCA. So you don't see that there is a necessarily better performance of doing this, like say, orthogonal random projection or Oracle PCR or in the limit. So, I mean, at least for these simple examples, it seems to me that they don't provide that much more. But yeah, we can see that. And the other thing that I wanted to discuss is that these results are very highly dependent on how the new features are generated. And it's not very clear that more features will help your regression. There's some examples. There's this classical book by Jane in 1982, where they provide some examples where, like, if you generate more features, your predictions become worse. And this discussion and this idea of like, what does it mean to have more features is discussed in this recent book by Bartlett, Montanari, and Rackling, that is the statistical theory of deep learning. Okay, so I'm gonna very briefly describe what we proved. We basically can prove a bias bound and a variance bound for the PCA-OLS, a non-asymptotic bound, and it's a matching bound, upper bound and lower bound. And yeah, it's similar to what you would get from the rich regression analysis. It's a little bit different, but not very different. And then the way you would prove it is by using the concentration of the empirical eigenvalues around the model eigenvalues. And yeah, and that's it. And we also use this concentration of empirical covariance matrix around the model covariance matrix. And some of the techniques are very similar to a paper by Bartlett and collaborators that is called benign overfitting. And that's something similar in some other setting. So, okay, so I only have 3 minutes left. So I wanted to briefly discuss how can one make the number of features go to infinity, and how is that connected with the Gaussian processes? So I'm just gonna maybe show you one picture for here. So here I'm doing this feature embedding model where I have some basis functions that look like this. there are Fourier bases, and I'm going to interpolate some functions using these basis functions. So the features here would be the evaluation of my basis functions in my different test points, and that would be the x's, and the y's would be the values of the function. So if I do that, then what you obtain is a picture of this form. So here, if I make the number of basis function very large, then I get this interpolation that perfectly interpolates all the data, but the function is basically zero. It tries to be the zero function. The reason why this happens is that when you do ordinary least squares, you're looking for the minimum norm solution. And in this Fourier context, the Fourier coefficients will have the same norm as the Fourier as the function. Like if you look at the Fourier transform of a function, it has the same norm as the function. That's Blanchet's theorem, I think. So then just minimizing the norm of the Fourier transform is basically minimizing the norm of the function. So that's what you get. However, if you do something like what people do with weighting the features, and I think something similar to what Laura was discussing before, but not the same. If you do some weighting where you weight your basis functions that are that have high frequencies with a smaller weight, then say that your weight decays like 1 divided by W squared, where W is the frequency, then you obtain a very smooth interpolation. And that's something that has been analyzed in some of the papers by Rachel Ward. If you do that, then you obtain this. So basically the reweighting of the features gives you like a smoother form of doing this interpolation. And the choice of how you reweight your features is related with using a kernel for your regression. So in particular, one way of this way of reweighting my features that I chose here corresponds to using a kernel called the Matérn kernel, which that is something that is widely used in Gaussian processes. So then in this case, I would say that an increasing number of features, depending on how you increase your features, you get different things and different models. And so it's not clear what a picture like the double descent would tell you if you look at the x-axis of what does it mean to be increasing the number of parameters or increasing the number of features. And in particular, if we look at this problem, we have with these weighted features that I just show you, we have this thing where like if we have and the number of parameters be between this regime, then we get that the mean square error blows up and then it goes down again. And in the limit, you obtain this behavior of this Gaussian process that you may think as like a non-parametric model. So with that, I'm going to say that take home message, we discuss how does the double descent appears and how you can remove it with regularization, in particular PCA or bridge regression, and how, well, there's a thing of like, if you have fewer points than dimensions, then you can give weights to your points and get weighted like least squares. And if you have more dimensions, no, I say it in the opposite way. Like if you have more points than dimensions, which is a classical setting, you can do like these weighted least squares that was described before. And if you have the opposite situation where you have more features, you can reweight your features and get a different regression model. Yeah, so this is my papers, and thank you for your attention and the invitation to this workshop.